Welcome, folks. Just testing to see if I have any echoes. If you give me some feedback in the YouTube channel, it would be good. In the text chat. Should clean up my mess here. Too much mess to clean up. I'll just leave it. See if I got another video I can play. Let's see here. Let's see. Okay, thank you all. Hi, just ramping up here. Jonathan says we'll start the presentation in a bit, around 7 o'clock. So this part of it will be whoever gets on Discord wants to chat. We can chat for a little bit. Let's see here. Yeah, okay. Let's see, what other?
Oh, test check.
Hello. Is it working? Okay. Hopefully I've taken care of any of the echoing stuff.
I don't hear myself at all.
Okay, good. Just going through some of my little short asteroid and comet videos. Do you want me to share in Discord? Sorry, I didn't hear you.
I guess it's up to you. If it makes it easier.
Well, I'm broadcasting directly to YouTube, but I'm just saying anybody, you're the only one in Discord right now, so you can either watch it on YouTube, which is where it's going to be broadcasted anyways, or I can pop it up here in Discord for those who want to watch it locally.
Easier to send people to.
Pardon me?
It'd be easier to send people to YouTube.
Yeah, exactly. But I can put a live feed up here for those that are only here. That's whatever. So yeah, because I won't be rebroadcasting video from anybody else. So this is for Discord here, is just really for the audio. Let's see here. You put on there I'll start processing a demo in about 20 minutes. I'm assuming that's still what you want to do. I should show some of my time lapse. I've got those as well. Let's see here.
A little bit late in getting dinner underway, so I'm
So this is as the asteroid Florence back in September 2017. It was when it went by closest approach to us. So that one.
bright.
Pardon me?
It was bright.
Yes. Well, it was close. It was when it went by its closest approach, and I tracked it for over 4 hours. So that's why I've got so much data on it, and you can see how much it moves. The first segment was tracking on it, and now this is just normal tracking on the stars and watching it go by. But I figure in 2 hours or in 4 hours it traveled about 2 degrees. Degree and a half to 2 degrees is approximately.
Crazy.
Yeah, it was moving quite
Remember,
quickly.
there was that little tiny asteroid that passed between like halfway between the Earth and the Moon in 2017, I think, in like January, and that was really booking it. That was that and Comet Lulin were the only things that I've ever seen actually move in an eyepiece, other than during occultations or whatever. But something.
Oh, I haven't looked at some of these in quite a long time. This one, what is this? Oh, nah, I'm not going to do that. Let's see. I guess that's good enough. So, let's see here. All right. What I thought I'd do tonight, Jonathan, is show processing the Crab Nebula, M81, and then the comet. We took that night. We also took about 20 some frames of comet 2019 Y4. So I can show you how I process that. It's a little different than stacking regular data. It's a different procedure I follow. That's what I thought I'd do tonight. Let's see here. So we got 9 people on YouTube right at the moment. I'm going to bring up my tools here. We'll go over the tools I use and why, because there's multiple ways of doing this.
A frame.
Sorry, what?
To skin a cat. More than one way to stack a frame.
Yes, there's more than one.
Per se.
There's more than one way to stack images. That's right. And I was actually in another meeting this afternoon with the astrophotography group. Gordon Hansen had demonstrated a couple of things in which I haven't used yet. I'm not. Maybe sometime in the future I'll use that technique, but I haven't had that use that technique. So it was pretty interesting to see how he's doing that. But there were 6 or 7 of us. I think there were 7 of us in a meeting this afternoon at 3 o'clock on WebEx. So we shared a couple of pictures each and all that, and then he showed how he did some minimizing the size of stars and enhancing their color. Was what he talked about today. But let's see here. We'll throw up a little agenda here. DSS, Deep Sky Stacker. And PixInsight. I'm only going to show one of the 2 methods for stacking DSOs, and then I'm going to use the other tool for stacking the comments. They both do both, but I found it easier to do one in one tool and the other in the other tool. So this would be
Getting the dinner bell.
Okay.
Silent alarm.
Let's see here. So Yeah, I guess that'll be good. Let's see here. The short list. I'm just building a little short list of what I'll go over. All right. I'll bring this over here. And by the way, if you're on the YouTube channel and it looks fuzzy, the text, go to the bottom of the YouTube video and the little gear icon should say HD on it. If it doesn't, click on that gear and set it to either 1080p or 1440p for the highest resolution. And looks like my live feed stopped on Discord. That's interesting. Huh. I don't remember turning it off, but that's okay. Let's see here. Hello, Fred. So again, if your resolution isn't very good on YouTube, look at the gear at the lower right-hand corner of the video and set it to either 1080p or 1440p because I'm broadcasting in 1440p. I don't know if this font is big enough for you, but we'll make it a bit bigger here. There we go. So I'm going to go over that, these components of the tool. Objects that we'll work on tonight are M1, Grab Nebula, M81, the Bodes Galaxy. And then I'll show you how I do Comet stacking with Comet 2019 Y4, otherwise known as Atlas. And a lot of times these names are just from the observatory that discovered it. And so there's a whole bunch of Atlas comets out there and a whole bunch of Pan-STARRS, etc. So and the email that's sent out said we'll get started in about 9 minutes on the tools. And while I'm setting that up, let me go to M1. And first thing I'm going to show you is the fact that I've been taking M1 for 2 years. In the February of 18, March, December of 18, and then February and March of this year. And I have all kinds of different versions of it, depending on when I took it, etc., etc. So, Ken, that's up to you. If you're in Discord and it's annoying, go ahead and mute YouTube. Otherwise, you're going to hear me here immediately, and then 20, 30 seconds later, you'll hear me on YouTube. So it's up to you. And I'm only just in Discord in case anybody wanted to come in and chat. So, by the way, anybody that does come into Discord and gets on the audio, you will be recorded on the YouTube channel. I've got the audio coming from Discord to me back to the live stream to the Warren's YouTube channel. But anyhow, the data we'll use tonight was what we took last Saturday, and I processed these and published it. I just used just this data that we took, so I wanted to show you that even if you only take 30 minutes of data, you can still get decent results. It's still a little noisier than if you took a couple of hours, but that's neither here nor there. And I'll show you how I process that. And by the way, when I show you how I process that, it's probably going to come out a little different, but that's the the human involved. The the human's the most inconsistent part of this process. So let's see here. So I'll go over a little bit about how I collect the data and why, and before we even do the stacking. So just talk about what raw data is and darks and flats, and because I'll be using them during this processing, so I need to explain to you what we're doing with them and why. In fact, I bet you I have one here. Let's see here. I think I've got an example. Yeah. This is what I'll explain this too, because this is a flat. And this the part of the explanation is the flat takes out gradients and artifacts that you don't want in your final image. So we'll use that as well as part of the conversation. I gotta make sure I gotta keep these up on. Let's see what I want here. This one. Yep. Okay. So I can see the text in both of these. All right. So it's 5:02. Let's see, what do we got on the YouTube here? We've got 8 people on YouTube. All right. I think, go ahead, Ken. I see you're typing. No, I'm not going to show any bias. No dark bias or dark flats. I have yet to use bias. Maybe I should be, but I have yet to use it. And one of the things as part of this talk, I want to explain that I'm going to do rudimentary processing, nothing very advanced. I consider my results kind of intermediate. There are much better image processing people in our midst here in Michigan that do outstanding processing data. I've gotten into a routine of basically using what I'm going to talk about today because it's quick and it's reasonable. What I consider reasonable for my purposes, the results that I get, and people like Bill Beers and Jim Bernard and Doug Struble and Chris Strang and other people in the astrophotography groups. They do a lot more specialized processing that I have not even addressed yet. So tonight's talk is going to be basically what can you do in a kind of a fairly straightforward manner to get some decent results. And the fact is, when I do my comet stuff, I hardly have to do any real processing of that. That's just I gather comet data just for the purpose of gathering its position from night to night and its change in position from night to night, and to see if the tail's growing and the coma's growing, and is it getting brighter, things like that. Some of that data I'm going to use for some astrometric purposes and photometric purposes, but that's a whole nother talk. Yeah, Ken. I actually do some DSLR work too, but it's all wide field for my time lapse. That Great Lakes Stargaze time lapse I did at the beginning. I don't know if you saw it or not, but in any case, um, I'll do a little processing on that too. And I guess what I should mention is the equipment I use to collect data. And let me pull up a picture of that. My telescopes. Let's see. What should I use here? I have a, yeah, this should be good. Yeah. So this is the equipment that I'm using. It's a 10-inch Ritchie Chrétien on a Lost Mountain DG11 mount, and I'm using. I have two ZWO 071 cameras, a Lodestar camera, a Canon T3i that's piggybacked on top. This system is fully automated, and I can run it. I can run it from my house. The laptop on the desktop is what runs the entire system. So I just remote desktop into that laptop to run this thing. And I can set up a script so it'll run all night, and I can go to bed while it's running. And it handles everything. It does automatic focusing, automatic meridian flips, reacquires the data, plate solves to reacquire positioning, the whole 9 yards, and then it parks itself when the sequence is done. So that's how that works in the morning, or when I'm not awake. Last Saturday I did everything ad hoc, and I was live with that. And then when we shut down at 12:30 last Saturday, I had two more objects that I put into the sequence, and I let it run while I went to bed. And that was M81 and I think it was M101. Is that the two I get? Yeah, something like that. Maybe I don't remember. There were two objects that I got in the morning hours. I'd have to go look at my list here. Was it M106? Was it no 101? It was M65, and then M101. Those are the two that went in the morning after we shut down the feed. So feel free to put questions in the text chat as we go along. So anyhow, that's the telescope I used for that last weekend. And so we'll get started here. Now, during the data acquisition, the 071 camera is a one-shot color camera. It's the size of an APS-C chip, which is basically 23 millimeters wide by 17 millimeters high. Okay, so it's a rectangle, 23 by 17 millimeters. And the scope is running at 2,000, approximately 2,000 millimeter focal length. So the images that I take that we saw last week are all raw lights. And those raw frames are all in what's called FITS files. And we're going to go here. And we're going to bring up M1. So last week, all these little blue diamonds that you see are the FITS files, the raw data. And we took each of these were 2 minute for subframes, and we were at a gain of 300, and the camera was cooled to -5C. And we took I think 20 of them, or 15. We had 15 of them. Yeah. And so we only ran about 30 minutes on this object. But previously, last month, I took darks for 5 different exposure times: 1 minute, 2 minute. In fact, let's go here. Go to my dark frame library here. We took 1 minute. Maybe I should make these bigger. Yeah, I guess I can't make that bigger. 1 minute, 2 minute, 3 minute, and 5 minute exposures at a gain of 300. And the way you take darks is you can do it anytime. You just cover the scope, and you set up a script to take your exposures the same length of time that your lights are going to be. So 1 minute lights, 2 minute, 3 minute, and 5 minute. That's typically the 4 exposure times that I use for my objects. Sometimes I go less, like 30 seconds for brighter things. So you set up all those darks, and in this case, we're going to use 24 darks for this first processing. And they're all 2 minutes. And then the flats, you take those whenever you change your optical system, in other words, if you take the camera off, fiddle with your system, and put a camera back on, you're going to have to take flats again to eliminate any of the gradients. And gradients are things like dust donuts. Um, here's a worst case scenario I took last year. Where is it now? There we go. Of gradients. All these little rings or dust donuts that are part of the optical path somewhere. There's some bigger rings in here, which means they're further upstream. And I know where these dirt donuts are. These that are about the size of a 1 inch on my screen. They are on the filter, the UV IR cut filter. That is actually no. These are on the AR window. That's approximately 17 millimeters in front of the chip. These bigger ones are on the UV IR cut filter that is approximately 41 millimeters in front of the chip. The big donut is the obstruction. The big donut is the central obstruction of my telescope. And then off in the corners is vignetting. And these flats, in fact, there's a huge donut over here that is probably a speck on the on-axis guiding port mirror. So I have lots of surfaces that a dust donut can show up that's fairly close, relatively close to the chip. The on-axis guiding port's about 60 something millimeters off the chip. Anything that's on the primary or secondary mirror never shows up. They're just too far away and not even focused. And these are getting closer and closer to the focal point. That's why they show up. So that's a flat. And the reason you take 50 of these is so that you can effectively subtract all these artifacts out of your final image that will be there in the dark frame or the light frames. So that's a little bit about the flats, why you take them. Now, granted, I take flats. It makes me lazy, so I don't clean the the optics as often. But sometimes when you go to clean the optics, you may get rid of some of the artifacts that you saw there, some of the dust donuts, but you may introduce other ones. So it's kind of one of those things where you say, well, if it gets bad enough, I'll clean it, but I'm not going to worry about it right now because my flats take care of it pretty well. So those are 3 elements that I use for data acquisition. There are people that use bias frames and dark flats, and I have not gotten into those 2 and don't even know why you would use them at this point, so I'm not even going to address that. But like I said, I'm talking about beginning to intermediate data acquisition and processing here tonight. So once we've acquired that data, we want to put it together and process it. And part of that is stacking. And what does stacking do? I'm going to stack 15 images here of M1. So I'm going to pull up the M1 data that we took last week. Let me get this details, type. We're going to pull up the FITS files. Okay, there's 15 of them. And I'm going to do this stacking in oh, I pressed the wrong one. I'm going to clear those, clear list. I'm going to do this stacking in Deep Sky Stacker, and here's the reason I'm doing it here. In Deep Sky Stacker, you load up the lights, the darks, and the flats. And if you want, you can check every frame in a FITS viewer, or even right on here. When you load them up, you can look at each one. If you want to negate any one of them that looks like a bad frame because it's drifted too much, the stars are oblong, or you have a big satellite go through, you can remove them and not stack them in the frame. Or you can tell it to stack some percentage of the frames that you have. So let's say I have 100 of them, and I want it to stack the best 80%. So I can set it to 80%, and it'll stack it scores every one of them by some algorithm it's got, and it only stacks the best 80% or best 50%, whatever you're going to do. In my case, I have my system set up so that if the only time I would have to remove one is if during an acquisition I got clouds rolling in over it such that it acquired the data, but its background got very bright, and it kept it. Because right now I have the system set up so that if the guide star goes more than 2 pixels out during guiding, it will throw that frame away and start it over again. So I almost always have 100% good frames as far as tracking is concerned. The only time I have issues is if I get some satellites through, or some high Cirrus that comes through, and I kind of want to throw away those bad ones. So I may go 80 or 90%, because it'll throw the low scoring ones away. So anyways, we're going to open up these 15. Then we're going to open up our dark files. So I'm going to go back to my dark library here. And these were 2-minute exposures, so I'm going to pull up the 2-minute darks. There's 24 of those. And then I'm going to open up my flats. And with a new alignment, yeah, this is the set that I want. There's 50 of those. By the way, when you take your flats, my dynamic range is between 0 and 65,000 A to D counts, or ACUs they call them. And I try to take my flats right around 20,000 or between 20 and 24,000 ADUs. And the way I do that is, as they're coming off the camera when I'm doing the flats, is I just put my cursor around on the frame and look at the ADUs counts at the bottom. And yeah, okay, that's what I want. And then I run a 50 frame run on for that setting, and then I'm done. So I'm going to open these. And I did these flats back in February because I don't change my system. It's in the observatory. I never touch it. So these flats are still good. So now, if I scroll up here, you'll see that I've got my M81 shots. Why is there only 10? I thought we had 15 of these. Did I miss them? M81. Oh, I was going to do M1. That's why. My bad. Do M1 first. That's what I meant to do. There we go, M1. So I'm going to pull these 15 up. And I'm going to get rid of these M81s. So I'm just going to highlight them and say remove from the list. Okay, so M1 is down here at the bottom, and there should be 15 of them. So when I check all, it should pop up here and say light frames 15. Good. So that's what we want. Now, if you look at the raw data, I'm looking at the raw data right now. This is what a single frame looks like. And I'll maximize this now. So a single frame looks like unstretched or anything from the FITS file. So this is what the raw data looks like. Oops. Gotta make sure we do this right here. There we go. This is what the raw data looks like. Hi, Diane. This is the crab then. Raw data, unstretched, unprocessed. Just a single frame. And I'm looking at all these right here. So they look okay. We're going to use them all. So at this point, they're ready to go. I'm going to say register. And I'm going to say use 100% of the pictures and stack them. So we'll just let that run. It'll only take a minute here. So it's going to register the 15 frames, which means it's looking at all the stars down to a certain magnitude, matching them all up against each other, against one master. It picks one of the highest valued ones. And then it's going to stack them all. So right now it's registering them. And now it's going to stack them. And at the same time, it's applying the darks and the flats to each frame. So it's doing all this work for you just by hitting that register check picture. It's registering them, applying the darks, applying the flats, and stacking them. And it's going to create one output file. It's a TIFF file that I'm going to then use in PixInsight. And the reason I use this tool is in order for me to do this in PixInsight, they do have a pre-processor now that does a lot of this, but it's still a multi-step process. Oh, the other thing DSS is doing here is it's debayering it. In other words, it's creating the color image too. When I had to do this in PixInsight 2 years ago, I had to debayer all the frames. Then I had to stack all the had to register them all, then integrate them all before I could start processing them. And that took a lot of time. This does it all in one shot. And that's the reason I use it. And I don't use Deep Sky Stacker to do any processing, just do the stacking. It's doing the 3-channel alignment of the colors. And saving the image away. And then it'll display the stacked image. And the stacked image won't be processed. It'll be stacked. So I've taken all 15 frames and put them together. And when they stack using an average or a median, depending on what you want how you want to do it. They don't add data. They don't add, because if you did that, after 20 frames, your entire screen would be white. They average the values. They average the values out. So there's the stack image there. If you remember the single frames that we showed you, they were FITS files. This is a stack and it's in color. Okay, so that's before I even do any processing. That's actually kind of nice. Now I'm going to go over to PixInsight. And we're going to maximize this guy, and we're going to open that file up that was just created. Let me make sure I'm on schedule here. What do we got here? Stacking. Yeah, so you can stack in Deep Sky Stacker or PixInsight. And I wasn't going to go through the stacking process in PixInsight. It's doable. I just prefer using Deep Sky Stacker. So in processing, we're gonna pull it up now and do these five or maybe 6 functions. We'll see, and it really depends on the target. So we'll go here, M1, March 21st, and autosave 001.tiff is the file we just created, and we'll pull that up. Now when it comes in here, it will be the raw stack with no processing, so it's going to be dark. And I'm going to show you something. I'm going to do an auto stretch, which means it's going to maximize the stretch without any intervention. It's an automatic auto stretch. And what you're going to see is that it's going to have this big old green background, and that's because it's an RGB Bayer matrix. Two greens with an R and a red and a blue. And that's how it comes out when it's debayered. So what we'll do is we're going to take this and we're going to apply, the simplest case is we're going to apply automatic background extract, which basically does a color balance, a somewhat color balance, but it normalizes the image and takes out some of the gradients. So let's go ahead and hit this, and then we'll see what it looks like. It's going to create a new file in memory. Hopefully you can all see this okay. Okay, so it just created a new one. I'm going to do an auto stretch on this. And there you go. So the green's gone. Most of the gradients are gone. This is a little bit overexposed as far as stretching is concerned, but that's a max stretch. And that I do that real quick just to see how it worked out. And this will be fine. There's another couple of tech tools called Photometric color calibration. I will use that to get a better color balance because what it does is it uses the stars in the field of view against a database that has photometric data for a lot of the stars and uses a reference point to give a better true color calibration of the object and the surrounding stars. But the simplest thing is this auto background extract gets the color balance somewhat close. Now we'll minimize this. I'm going to do one other thing. Now I'll do that in a minute. I can show you. I can back up. So we'll go to histogram now. So we've done the auto background extract. I should show you the color calibration. I'll show you what that does. So let me do that. So I'll bring up color calibration. I'm going to do the simple color calibration. And what that is you identify an area of the screen that you want as your primary color and then your background color. So I'm going to pick Crab Nebula and some of its surrounding area. In fact, I'm going to move it. Oops. That's not what I wanted. Hang on a second here. Delete all. All right, so I'm going to pick that star, and this object as part of the foreground. And then I'm going to pick a small area over here that's kind of part of the background. And then I'm going to go into the color calibration tool and identify those for this tool. Preview 1, preview 2, and then we'll just hit the little rectangle or the square and say go. So it's going to go out here and it's going to do some magic. Okay, and now when I auto stretch it, we'll see what it looks like. Now what it did, it moved it a little bit into the blue, out of the green into the blue. So that background is actually a little bit more, it's subtle, but it is, I can tell that it did change it. It's got a little bit more blue in it now. So if you like that, again, when you're processing data and you're a different user, five different people processing the same data, probably will not get the same results. A lot of this is art. So anyhow, I'm going to turn off the auto stretch, and then we'll do an actual stretch, and that's with the histogram here. So you'll notice I'm going to bring these little arrows that are in the graph. I'm going to use them to stretch the data here. We hit there. Okay, so now we got that so far. I'm going to bring up the bottom a little bit to get it darker. Bring the top down to get a little lighter. As you can see, you can start seeing the filaments in the crab now starting to show up really kind of nice with a reasonable color balance. It's not purple, it's not green, it's kind of a reddish that you would expect. Yeah, maybe we'll go right about there. So this is art too. Do you want to have it real bright in the background, or you want to have it real dark? So you'll kind of pick a spot that you think is reasonable. Again, that's art. So I like the little darker background, as long as I don't lose too much of the data in the nebula itself. So I'll hit that. Okay, so that's the histogram, simple stretch, and we're going to go to the curve transformation. We'll do curve transformation here. And what I'm going to do here is I'm going to use the saturation. So watch the color in the nebula as I move this. See how I can increase the saturation of the colors of each of the objects, including the stars. I mean, the red stars are getting really reddish orange, and the blue stars are getting bluer. The red in the nebula is getting redder. I can make this so extreme that it looks clownish. So there's a nice clownish look at it, right? But what I like to do is keep that a little more subtle. So I've increased it just a bit to get so you can tell there's color in the stars. And I usually hit it right there at this one spot almost every time, because that's kind of how I like it to look. In fact, the blues in the nebula comes out a little bit too. So if you notice in the histogram, the blue spread out and dropped down. So there's a lot more blue in here now than there was before. And there's not much more I do in the color. Sometimes I may mess with the luminance a little bit just to brighten it up or darken up the background. So you can play with this and do all kinds of stuff. There's here I'll make it really dark, right? Really dark background. Again, this in my mind, this is all personal preference. How do you want it to be rendered? So I like a little bit darker background, so I did that. And if you saturate the top end a little too much, it blows out the middle of the nebula. So you want to kind of careful about that. But we'll just darken it up just a bit. There, about right there. Bring the top up a little bit. And it really depends on how it looks. So I'm going to zoom. Let's see here. I'm going to shut off my previews here. I don't need them now. I'm going to zoom in here, and as you can see, you get in here really tight on a zoom. It's pretty noisy, but it's also not very sharp on the little filaments. And I'm not going to be able to get it much sharper. I'm pretty good focus. All the stars are nice and round, and they're good guiding and everything like that. But I don't think I'm going to get it much sharper. But there are some fun tools you can try. Here's an unsharp mask. And unfortunately, I can't zoom in to show it here, but you can sharpen up the image, but it introduces noise. You notice if I back this off, the nebula gets pretty soft. If I go extremely here, it gets a little sharper, but the background looks, it looks like you've thrown pepper on it or something. So I don't use this very often, but once in a while I will. At this point, I'm going to leave it alone, but I wanted to show you what it would do. And what I will do is I'll execute a simple, because I can always back this off, but I'm going to execute this unsharp mask, and we'll see what it does to the nebula here. When you look at it, it'll if you watch it carefully, once it's done, it'll look like it just added noise to it. It didn't look like it did much, but add noise. So I'm going to Control Z, which takes it away. Okay, so it softens up a little bit. The other tool that I sometimes use is the deconvolution. And I just use the defaults that are on here. So, and I'm not even going to go through what they are because personally, I don't even know. I just like what it does sometimes. So I'm going to execute that. It'll take about 20 seconds to run through this. But watch again the filaments of the nebula. See if that actually improves it at all once it gets finished. And like I said, this is the simplest process that I've come up with for doing my process. As you can see, I've already got the data really where I want it. And now I'm just going to look at some tweaking things that I may or may not even do. The unsharp mask, the deconvolution, I may not even use it for this object. Sometimes it depends on what the data set looks like. And some of you know I've taken data all the way up to 12 hours. Not intentionally, but I have. It did introduce some noise, but it did sharpen up a couple other things. But I'm going to go back it off, look at it now, and then I'm going to back off what it just did. Okay. It's almost no change. So in that case, if it's no change, I don't want to add anything to the data set. So I'm basically done with this. And what I usually do is I save it away as an EXIF file, so it saves all of the changes I made that I can use again from that point forward. And as a matter of fact, I've got one sitting here already, and I'm going to call it second processing because it's a new processing. And what I'm going to do is I'm going to pull up the other processing between the two, and we're going to look to see how much different I did from the last time. And I think I did it differently. So let's pull up the old one. Yeah, from a week ago. And let's compare the two. Okay, yeah. See, I can already see what the difference is, right? The new one I just did has got a darker background, right? So that's what you call variability of the user. But it's got similar color. The background's a little darker in the one I just did than the one I published a week ago. And that's one of the problems. You get a human involved, it's never the same. This one looked kind of good for me when I looked at it last. Actually, this one looks different. The little color balance is a little different too. So anyhow, so those are the two things that can look different, just based on what you did that night. And I have another example of that when I did my M81 before last week. I did another version of it last month and the month before, I think, or whatever. I compared what I did before to what I did last month. Totally different color balance, and I did that on purpose to see what the different technique was using the photometric calibration or color calibration versus not using that, and the color balances was completely different. And I published that on the Warren Club Facebook page, the two. You can go and look at those. So what I'll do now is I save the EXIF file, and then I save a JPEG version of it. And the reason I'm going to do that is I'm going to show you I have one more tool that I use that's outside of PixInsight. PixInsight has a tool to do this. I haven't discovered it yet, and I haven't used it yet, but I know it exists because other people have talked about it using the noise reduction tool in PixInsight. I've just never bothered with it yet. This is one of the fun things about getting into this. I've been imaging with this setup now for 3 years and these tools. And every time I do this, I learn something new every time. I learned something new today in the other meeting I was in. But what I wanted to show you is I have this tool called Topaz Labs Denoise. And I wanted to show you what it does. So I'm going to pull this up. Going to pull up this new JPEG file that I just created, and it's second processing. It's this one right here. So this is an added starter for your enjoyment here. And what it's supposed to do is eliminate some of the noise, right? So I'm gonna hit this auto button and see what it does. So if I go back and forth, it supposedly eliminated some of the noise. What I found is sometimes it does a really good job of this. Sometimes it actually makes the noise worse. I'm going to slide that bar over, and now you can see on the right-hand side where, it gets rid of the noise, but it makes some really dim stars look really goofy, whereas the stars are not so goofy looking on these dim ones. But it does smooth it out, and I'm not sure. I don't always use this, but sometimes I do. If I've got 4 hours of data, I almost never need to use this. That was just an example, and I'll save it away so we can take a quick look at it in regular view. Because in this zoomed in view, it's not very useful. So it's actually doing the entire image now. It's processing that image with that setting. And I actually I slid that remove noise bar quite a bit more than I normally would do because I wanted to see what it does in the final image. %. Any questions so far? Text in either YouTube or in the Discord. Not too much in YouTube right now. Okay, so I'm going to close this window. And I want to look at this data now. One. Okay, let's slide through this data here. This was the one I just processed tonight. Here it is in through after the denoise. I'll go back and forth on it. There's a slight change. I think it gets blurrier, less noise but blurrier. So that's yeah, Ken, Topaz and JPEG. I think it can read TIFF files too. So I would keep the original and not use the denoise on that one. But here's the last week's processing and last week's denoise. So it's a very subtle difference. Hi, Riyadh. So that's basically that's the Crab Nebula that we just we took last year or last week, and I just processed it again. Any questions about this? Okay. Well, um, I'll let the YouTubers catch up here. As soon as I see it show up there, then I know the question's being asked. I've used up 35 minutes. So I don't think I'll do M81. What I think I'll do is show you what I do with the comets, because I do a lot of comet work, if you're interested in me doing that. Silence. Okay. I'm going to close this. Close this. I will use the comet from last week, and we'll just go through a quick demo of that. So the first thing I do is I pull up the debayer tool. I set my mosaic pattern to RGB. I add the files, and this is the these are the files I had. So I add all these files into this and then execute this process. What comes out of it is a list of debayered files. You can see that there's a D at the end of the file names here. That means they're debayered. So that's what adding the files in here and then just executing it to an output directory. That's how I do that. Okay. I'm not going to go through it. It takes a little bit of time. And then once the debayer is done, which means I've turned them in those files into color, they're now color, I use a tool called Comet Alignment. And I'll add the files under the debayer. I'll add these files in like so. I pick an output directory, but the very first thing I do is I take the first frame of this object. I'm going to do an auto stretch so I can make sure I got the comet in here. So this is a raw debayered file. And I highlight the core of the comet. The first frame, and then I scroll down to the last frame, stretch that, zoom in, and then I highlight the core of that frame. Now the assumption is in here that every one of these frames are the same length and they have approximately the same pause in between each of them, so that there's a delta value that's associated with every frame. If you mark the first and last one, it knows what to do with it. And once you do that, you hit the go button. It goes through all of those, and it registers the comet cores in all 10, 15 frames, whatever the number of frames are together, and writes those files out to what I call an alignment directory. Okay, so once the alignment's done, I'm going to close this. I go to a tool called Image Integration. And that tool, I pull up those alignment files, which are in this folder here. There's 10 of them. And I just hit the go button. And I'm going to let this one run. This is going to take all of those files, 10 files. It's now stacking those 10 files on the core of the comet. This will take just a minute. It's almost done. Yep, now it's 1, 2, and 3. Be done here in a second here. And what that does is generate a final image file for me to now process, just like I process a regular deep sky. The only difference is this file will not have the darks and flats associated with it, so you're going to see some artifacts. So if I do an auto stretch on this, as you can see, it's got green background just like we had before. So I'm going to go over here and I'm going to hit my automatic background extract on this file. And now I have this file, which is basically color balanced in the background. And you notice it's got the big central obstruction donut on it, and it's got the vignetting. That's because I didn't apply any flats to this. And I'm not making pretty pictures here. I'm just kind of collecting magnitude and motion data. If this comet ever gets to be where it's really beautiful, it's got a blue ion tail and kind of like Hale Bopp, I'll do a little more work on presenting a pretty picture. But at that point, I'll be able to take really short exposures because it'll be so bright that I can apply darks and flats, and I don't even have to stack on the core necessarily. So, but this is what I do for the comet data. And I'll just pull this up in a regular histogram, and we'll stretch it somewhat. Like so. Kind of get a good dark background that I like. As you can see the coma is getting pretty significant, and there's a nice tail heading off to the 730 position. So we'll hit that. That looks okay. I'm going to pull up my color, our curve transformations here, and hit the saturation. Reset this, and I might pull that up a little bit to show the colors of the stars a little bit better. And of course, the comet itself will get a lot greener. But what that does is allows you to see the no, Ken, the green is because of the chemical makeup of the outgassing, cyanogen and something else, carbon. I don't might be oxygen. Each of them might be a little different, but the green comes from the outgassing, the gas that's coming off the core or the nucleus. No, the green sky behind it. You mean in the original one before I just did this auto background extract? That green sky comes from the fact that I'm using a one-shot color camera that has 2 green pixels and only 1 red and only 1 blue. So its de-Bayard pattern is going to be green. When you do the background extract or the color calibration, it color balances to a white balance. So the green goes away. Yeah. So that's why you have to do that. And I didn't even do a color balance on this. I just did an automatic extract. In fact, if I did a color balance on this, it'd be interesting to show you what changes. It actually, the comet gets a little less green, a little bluer. But anyhow, that's how I process a comet. Let me pull up the luminance here. In fact, if I look at the RGB, they're pretty stacked together there. Which is reasonable. The green's a little stronger on the vertical, but not as wide on the horizontal. But I'll go with the luminance here just to darken up the background just a tad. There we go. So there's a comet shot of Atlas. So that's my processing for comets. Any questions on that? And obviously, since I stacked in the core and the comet's moving through the 20 minutes that I took or 10 minutes that I took, the stars are going to trail. This gets even more. You can stack these comets in DSS. In fact, you can do it's a 2-pass stack in Deep Sky Stacker, where it will you identify where the comet is on every frame, and then when you go and run it through the registration and stack process, it actually does it in 2 passes. It will stack the stars, and then it will stack the comet, and it will slam it together. However, Deep Sky Stacker is a little undeterministic on how well it will do that. I've had it where it stacked the comet fairly well, but it kept, when it stacked the stars, it left black halos, not white halo, black halos around it. So what it was doing was masking off the star trail to the size of the trail and then putting a single dot back on there, which kind of gives you a weird side effect of having all these stars in the field of view that are completely black right around them, and the rest of the background is lighter than it. So it doesn't look very nice. So Atlas is about 8th magnitude right now. And it's going to get brighter. It's supposed to get naked eye. It's going to pass, was it perihelion on May? Let's see. May 23rd? I don't remember. I'll have to look it up again. But if you go to the Sky Live, you can look up all kinds of objects, including any of the comets, and you look it up, and it'll tell you what the JPL estimated magnitude is. And then it gives you a magnitude below that is what was actually observed by observers around the world. And this one is listed at 14th right now, I think, but it's actually seen it to be 8.2 or something like that. So I'd go with the observed one, because these images that I'm taking are 60 seconds, and that core is really bright. That's brighter. That's an 8th magnitude core easily. I mean, the stars I've got in these 60 seconds go down to at least 12th, maybe 13th magnitude, just the stars themselves. And it's only 60 seconds. If this was a 14th magnitude comet, it would be barely on this frame. So that's why I know it's not 14th magnitude. So that's my presentation for rudimentary processing. Okay, would you use the comet mode and pick inside the planet conjunctions with? I'm trying to understand your question, Ken. Ken's question was, would you use the comet mode in PixInsight for planet conjunctions with a DSLR or not? No, I don't see any reason to use comet mode in PixInsight. Conjunctions are not necessary for a 20-minute or lower total exposure. Planet conjunctions are going to be fractions of it, or seconds, not 20 minutes. You can use PixInsight histogram and curve transformation for any objects. So if you take a 5-second shot wide field or with a DSLR, you can use this histogram and this curves transformation on DSLR images, CR2s or whatever they are, raw data. Yeah, you don't even have to debayer them usually. In fact, I've got my T3I's CR2 files, and I just pull them in directly and then start processing them. Jonathan says, yeah, I see that. Thank you. Unable to connect to chat. Please try later. I don't know why that message happened there. Ooh, it's not letting me text chat. Oh, there we go. Yeah, it keeps telling me my video resolution's not optimal. I know that. By the way, is the video sharp enough if you guys got it on HD mode in YouTube?
Sorry, I popped out to the other room for a second.
What's that?
Popped over to the other room for a second.
Oh, okay. Any other questions at this point? Okay, so we've been going 50 minutes since I started the presentation. Been on a little longer than that, but and the final thing I do with these JPEG files is I put them on my Facebook and in my Flickr page. I spam the heck out of some of them that I think are decent enough to look at. Yeah. In fact, this comment is going to be in the newsletter. I wrote a little article about it. I think it'll be in the newsletter. So it'll come out in a week or so.
Be sure it will be.
Yeah, I'm not real verbose on writing articles unless I've got a story to tell. And a lot of times my storytelling in text is not very good. Usually I just get straight to the facts. This is what it is. This is what it was taken. You know, what the exposures were or what I took it with. He needs the Discord link. Okay, hang on. Let's see, where is it here? Is Dale in Discord right now? Let's see here. So I had a Dale show up on my list here. Oh, he needs it on YouTube. Okay. Hang on a second. Let me. I need to pull that out of a page here I've got.
Don't post it on YouTube because it might be permanent, and we don't want bots finding this chat room. So let me. I'll send him it in.
Okay. I want to save this. Just March 28, 2020 agenda. There we go. So that's the simple processing that I do for deep sky objects and for my comets. My lunar stuff's a whole different process. I do use PixInsight for some final color calibration, but when I do lunar stuff, I create AVIs. Is it AVIs? Yeah, I think that's what my ZWO creates as AVIs. They're really huge files for just 100 frames because the each file each frame's 30 some megabytes. And I take that, I bring it into not Auto Stitch, Auto Stacker 3, and I pull about 25% of the stack, the best 25% to create a final image, and then I just process it a little bit. In PixInsight, I do use the unsharp mask on that, but then I take the output of that and I throw it into Registack and use some wavelets to sharpen up some of my lunar stuff. And I'll just show you a couple of lunar images that I've got over the period of, let's see here. What do I got here? This is probably a good one to look at. So here's one that's not quite first quarter moon. And you can even zoom in on it a little bit. I think this one was a daytime one. I actually took a daytime shot. So I had to work with it quite a bit to get the background dark. But, so that's a lunar shot. Might have another one there. Yeah. This thing takes nice lunar shots at prime focus even, because the whole field of view is not, I can't fit the entire moon in my field of view. It's 27 arc minutes by 40 arc minutes. So on the short side, it won't fit. So if I were to take a full moon, I end up taking a mosaic of about 4 panels, and then this is other stuff that I do. I do plate solving of galaxy clusters. These are galaxy clusters that I've taken, and then I plate solve them to see how many gazillion galaxies are in the field of view. So that's what that's all about. It's just another thing that I do. So anyhow, and then this is a shot of my wide field camera that's piggybacked on the 10-inch. I got a 10 millimeter lens piggybacked on my Canon T3i, so I can keep an eye on the sky and how much clouds are coming in or stuff like that. And in fact, in this picture, you can see the Pleiades up there in the right, and the Hyades and Taurus right there, and then the Orion is right there into the clouds there on the horizon there. So kind of a nice little added feature. That's my skyline. That's looking that's looking over Detroit, about 50 miles away. Okay. So, any questions? Don't be shy.
Most frustrating object that you've worked on?
The most frustrating. Oh, well, yeah. I wouldn't say this is the most frustrating. This is probably the one object I've yet to be able to capture, if you want to call that frustration. And that's my asteroid. I actually tried 2 weeks ago, I think it was, because it's 18.5 magnitude. In fact, Tom, is he still in the channel here? No,
I think he
left. He was with me when I started imaging.
I was here too for that. Yeah.
Were you? Okay.
I believe so. I mean, it was the night you were going to work. Yeah, I was here for when you were trying to get it.
Yeah, I think I finished the comments and I said, "Well, let's go after the asteroid here." And I got down to the 16th magnitude stars, but the sky was so bright over there that I couldn't get any deeper than that. I have to have a really dark sky to get to 18th magnitude or 19th. And if the sky's brighter than that, I'm not going to see it. So no, I went back and looked on the charts and everything, and I looked at that each frame individually, and I stacked it and everything, and it did not. I was unable to acquire even a single photon, I think, of it. because I think the sky was brighter than it. So that's an object that if I go up to Boone, I can give that a shot because my southern horizon's dark. And really that's what it boils down to. I have to have a dark horizon. And the sky up at Boone is SQM is 21.5 or 21.6, somewhere in there, which means that that's 21.6 magnitude per arc second. So I should be able to get it as long as the integration time's long enough. And if I can go 15 minutes, I should be able to get it. And oh, by the way, it is actually moving quite quickly. I looked at it that night, and then I looked at it the next night on the Sky software, and it moves a lot. It actually moved out of the field of view in 24 hours that I had, so I had to go hunt for it, and I started tracking it. And it's moving quite a bit. So in one night, if I take a shot of it, let's say at 10 o'clock at night, and again at 2 in the morning, I'll see it move. I'll see the movement, and I should be able to, if I get the depth, I should be able to detect the movement. So, but most frustrating besides that, I actually find M42 frustrating. You know why? Because it requires really large dynamic range. The core of the Orion Nebula, the trapezium, so bright, and the little filaments way out on the ends are so dim that you got to take 5-second shots and then 10, 20, 30, 60-second shots and do some high dynamic range processing to get that to look what people have produced. My Orions are brute force. my Orion shots are brute forced, and they're just one exposure or two, and I just slam them in there. I mean, here's examples here, right? There's my Orion, one of them. Here's a wide field. So I don't even go after that. This Horset's kind of tough because you got these bright stars that are just out of the field of view. That and the red nebula is takes a lot of data to pull that out. That one's pretty tough. I think the toughest one is the iris. Let me see that I've done so far. Yeah, this one here was. Let me pull this up, and there's a lot of data on this one too. This is 122 5-minute shots. And I've processed the heck out of this one, and I've never gotten one that looks what I consider decent. But you can see the dark lanes around the outside and in the middle area. I've over-processed the heck out of it to the point where it looks ridiculous. It looks very clownish. This one, I'm not sure what to do with. Not sure how to make it look halfway decent. And that's because it's a lot of reflection nebula there and a lot of dark nebula. So that one's frustrating. Oh, if he's running, I'll go ahead and 8 o'clock. I've been on an hour. I can call it quits, and we can go talk. Listen to Jeff on Facebook. Does that sound like a plan, people?
Sounds like a plan. Are we? Unless you want to just stream his. Unless you want to stream his video for the people who are on YouTube who might not have Facebook. There's one question. Have you ever discovered a new comet?
Personally, no.
Also, Ken asked, what are you doing about the comet that's arriving soon?
The one that's arriving soon. I mean, the one I just showed you?
Think that's the one he may have meant?
Yeah, Y4. I've been imaging it all month. I've got 5 nights in it. Oh, Andromeda. Andromeda's way too big for my system. My field of view is less than half a degree. Less than half a degree, and Andromeda's like 4 degrees across one axis and about 2 degrees off the other. In fact, to give you a perspective. Yeah, I like doing this one. People ask me about M31. I say, so, do you remember where M110 is? It's right next to M50, M31. Right? Well, let me show you M110. That's my field of view with M110. And it's right next to M31. So that gives you an idea of size. M31 would, I could look at the core about, but if you look at any of these pictures where it's got M31 and M32 and M110 in the same field of view, and M110 is not very big, but that's what it looks like in my scope, and that's got two little dark nodules in the middle, etc. So this actually turned out pretty nice. So this is before I used darks and flats. I should do this one again.
Oh.
Okay, so I'm good. We're all set. I'll discontinue the stream and
Post it in the comments over on YouTube so people can join.
Did you post it there? You're going to? I can post it. I'll copy. Oops, no, I can't copy that. Why won't it let me copy that?
Post it on the.
I'll post it in YouTube right now. What Diane put in. I think that worked. Hopefully that worked. I don't know if that worked or not. There we go.
Actually, what we should see is if Jeff can join the Discord and present there too.
Whatever you want to do. My pleasure, folks. I enjoy it. I mean, it gives me something to do besides sit here and look at clouds out my window. Because for those people that don't know me, if it's clear, the observatory's open, and I've got data for over 3 years that I've collected well over 500 samples. So, but if it's cloudy, I sit here and process data, and I'm happy to do what I can to educate the best I can. So, what do you want me to do, Jonathan?
I mean, ultimately, it's up to you. I guess we could just leave a message that people should switch over to.
I think that would be
YouTube.
best. I think that would. You mean to Facebook? Right?
Yeah, unless we can get Jeff to project, but I think he's locked in. I don't think he's paying attention to the messages now. So
well, let me go look at what he's doing here. Let me just look at what he's doing here. Hang on. See if I can
just lift it off with a Saturn V.
Tonight, I don't have his link. That one's different than that one. So where's his? Let me refresh the Warren page here. Maybe I'll.
Let me invite you. I'll add it in the WASP page.
Okay. Where is it here?
This link might be better. Same link? It is the same link.
Okay, there's a just now. All right, for parts. All right, let me see if I can.
So we're coming up to the first stage separation. We're going to get a cool set stage sep again. Those motors that are going off, some of those, the ones on the first stage are called retros, and then the ones on the second stage are called ullage motors. So the retros are firing to try to pull that first stage away from the second so we don't get any collisions. And these little guys right here on the second stage are actually pushing the rocket forward because as soon as there's no thrust, all the fuel inside that tank is going to want to float. But you need it to go down into the engines. So those little motors give you just a little bit of thrust to push that fuel back to the back of the tank where it can then go into the actual rocket engine. So those ullage motors, very important during stage separations. Something you don't actually need in Kerbal Space Program, but I threw them in here just to make it a little bit more accurate. In this program, I'm using solid boosters. The Saturn V did not use solid boosters, meaning solid rocket fuel. They were little liquid motors. And I don't actually know the hard details on those motors, but they're small compared to the Saturn V. But if you had one by itself, it would be like the biggest model rocket you've ever seen. They are rather large when you take them outside of the Saturn V. So we're burning that second stage. It burns for a few more minutes. And now we're going to get the second stage separation. Again, we're going to get retros firing and ullage motors firing before we get that third stage kicking off. This is all happening really fast in this recreation. This takes a little bit more time. In the real Saturn V, they had what are known as interstage rings. So the stages weren't just 1, 2, and 3. In between 1 and 2, you had a ring that had to separate, and in between 2 and 3, you would also have this ring that needs to separate. And so the sequencing of all these events is a little bit further expanded. I actually wanted to talk about the launch escape system that you may have seen fly off right after the second stage ignited. There's a lot of cool things about that, but I'll skip it for now because we are going to be circularizing our orbit here. So this is, again, not exactly how the Saturn V would have really flown. Their ascent profiles, or the path that they take into space, is very well thought out and is done in a manner to not only save fuel, but to basically get you into orbit as you're running out of fuel. In Kerbal here, it's easier just to get up to a height and then circularize. So that's what we've done. But we've kept some pretty tight margins on fuel, trying to stay as true to life as the real mission. Now, I'm going to pause it just for a moment here and try to give you an overview of all the things that you're looking at in this video. So up here, we have basically our height above sea level. Over here, we have a bunch of information about our altitude and speed. Over here, we have details about our orbit. Apoapsis height is the highest point you are above the Earth or target that you're orbiting around. And then periapsis here is the minimum height that you're orbiting. And then over here we have the quantities of all the things that we're interested in. This monopropellant is what we actually use for attitude control. So where the spacecraft is pointing in 3 dimensions is controlled by little thrusters, and they are powered by that monopropellant. This is another thing I've never done in Kerbal Space Program. There is another way to control spacecraft attitude, and it's known as reaction wheels. And Kerbal lets you cheat, and it has reaction wheels with infinite torque. So you can just keep them charged, and they can always point your spacecraft. In reality, you only get so much torque or ability to maneuver out of a reaction wheel system. And most spacecraft use a conjunction of RCS, or this thruster system, and reaction wheels because you can use your propellant systems to then recharge your reaction wheels by spinning them in the opposite direction that you're spinning up with the normal chemical propulsion. And so you can get a little bit of extra life out of that. Then we have electric charge, so that's our batteries. This is another thing. The Apollo spacecraft, no solar panels. It is completely run by fuel cells, so we are taking liquid oxygen and hydrogen and converting that into, or liquid oxygen, separating that out. No, sorry. We're taking Yeah, we're taking liquid hydrogen and oxygen, combining it, creating water, and then also creating power. And so that is where we are getting our electricity. This ablator here is our heat shield. Save that for later. Solid fuel, those are those little rocket motors that we've already spent all of. And then we have liquid fuel and liquid oxygen here, and that is our main propellant. Then over here is all of our staging on the left. And then we have this nav ball down here at the bottom right. And this is supposed to be replicating a gimbal that you would see in a spacecraft. And it basically is just telling you which direction the spacecraft is pointing based on some sort of reference system. And then you'll see me pulling up other just kind of house cleaning things as we're flying the spacecraft. You can see the little RCS thrusters there firing, trying to point this spacecraft. And we are going to, now that we are circularized, it is ready to point, and we can make our translunar injection or insertion. This is the burn that actually takes us to the moon. This is using that third stage known as the S4B. It is going to boost our spacecraft up to a higher velocity, so much so that we can reach the moon, and then we are going to separate from it. And there's a lot of fun stories about the S4B that I'll tell you in just a moment. So here I'm designing a burn that is going to get me close to the moon. So this would have all been pre-planned by mission control, and you just execute the plan as it is written. I'm just kind of winging it. This is something that you can do in Kerbal Space Program, but you can't do in real life. There is no winging it when it comes to real space flight because you have much tighter margins on your fuel. All of these systems are much more complicated, and so you really need to know exactly what you're doing before you try to go out there. That's why there were so many missions that went to the moon that never landed on the moon, because they wanted to test every single system and only push the envelope a little bit at a time, because you never know what you're going to come across. So we are now fast forwarding to translunar insertion. This S4B third stage is going to fire us. We are almost pointed at the moon, but not quite. And you'll see in a moment, a lot of people think you point at the moon, you fire a rocket, and eventually you'll get there because it's space. You're just going to float. But that is not how orbital mechanics works at all. So you can see here, we're actually right down here, and we are pointed in this direction here. But that is not the direction we're going to end up going. We're going to end up going off in this direction. This is one of the weird things about, yes, translunar injection. That is one of the weird things about orbital mechanics. You're not free floating in space. You are orbiting a center of mass between you and the parent body, whatever it may be. And you can see as we fire a rocket, we grow faster and faster. It's going to slow down here as it gets to the moon. I'm using a lot of autopilots to do this so that I don't have to do quite as much work when flying the spacecraft. But there it is. That is the path we are going to take around the moon. We're coming in on the left there. That's going to actually slow us down, and that saves us fuel getting around the moon. This is what's known as a free return trajectory. If something goes wrong, we can just kind of loop around the moon and almost go back to the orbit we came from. Not quite true with this one. If you wanted to do a true free return, you would do it a little bit differently. But I am not planning on a free return trajectory. I know I'm going to make it. And in fact, on some of the later Apollo missions, they did not do free return trajectories because they knew that they could do it. So there we have the panel separation. So that exposes our lunar lander. We're now going to separate the command service module. So this is known as the command module. This here is known as the command service module. This is known as the ascent part of the lunar lander, and this is the descent part of the Lunar Excursion Module, or LEM, sometimes just called LM. Its technical name is just LM, but the guys at Grumman originally called it LEM, and they stuck with it. So now we're at the turnaround phase. So we are here in the command module. We are now going to turn that spacecraft around, doing this very slowly and easily. Those those thrusters have a way of kind of kicking you all over the place, so you want to do things carefully. This is actually way too close to the lunar module for turnaround. The real spacecraft would have separated by hundreds of feet, maybe 100 feet or so, so that they could really come in nice and slow and see where they were going. They did not have this external view that we have here. They're looking out very small windows, so you want to be very careful. Docking in space is about as hazardous as it gets. If you screw it up, you break things, and that is never good. So we're gonna very slowly, changing views here, we're gonna very slowly try to come back and meet up with the lunar module. Very slowly. Talking about that S4B, we haven't separated from that just yet, but we're going to. And in fact, some of the UFOs that were reported by Apollo astronauts were later figured out to be the S4B following behind them. They thought something was kind of out the window and they could see something following them, and it just turned out they weren't tracking the S4B carefully enough. In fact, on a much later mission, they discovered an asteroid orbiting the Earth, and they studied this thing a little bit, and it had the telltale signature of titanium, and then they realized that it was an S4B from Apollo 12 that had wandered out into a solar orbit and then come back in and was captured by the Earth briefly. And so that was pretty cool. They thought they found a second moon, and it just turned out to be more space junk that we've put out there. So now we are separating from the third stage. So that guy there is on a very similar trajectory to us. So it's going to basically be right on our tail the whole way to the moon. And in fact, on some missions, after they had left seismometers on the moon, they purposely put the S4B on a trajectory to impact the moon so that they could measure the moonquake caused by that impact. And what they learned from those impacts is that the moon is basically a solid body. It doesn't have a liquid core. It rings like a bell, meaning that when you have seismic activities, it oscillates through the moon much longer than it does here on the Earth, because on the Earth it is dampened by the liquid on the inside of the Earth. So now we're spinning around. This is a maneuver called the passive thermal control roll, or the barbecue roll. I did that just briefly, but in fact, on our entire float out to the moon, we would be in this roll. This is to keep everything an even temperature. If you just kept the spacecraft in one orientation like this, eventually you would cook one side, the side facing the sun, and you would most likely freeze some other things. So that passive thermal control roll is really important. Now, I'm going to pause briefly here. On the real Apollo missions, you can't just stay in that roll the whole time. You need to be doing certain things at certain points in the float or coast out to the moon. So you'd have to readjust your attitude, do a corrective maneuver at some point, and then go back into the roll. Or you need to be taking measurements of your location basically they would navigate by the stars as one form of checking their location, and then they would check that against the radar that they were using. You want multiple checks on what you think you're doing up here. So if the radar's telling you one thing, but your star measurements are telling you another, the star measurements, as long as you do them correctly, basically can't be wrong, and so there might be something wrong with the radar. There was actually, I believe, 3 different ways that they could figure out their telemetry or the path that they were on. So let's continue here. We have no mid-course corrections to make. We're going to come right into the moon. First time's the charm. We're coming in a little bit closer than the Apollo missions would have. They came in at about 110 kilometers above the lunar surface. We're coming in at like 40, but we're coming into a smaller body, so it really doesn't matter. We are going to be coming into the moon, and so now is where it gets dangerous. The next maneuver that we have to do is called the Lunar Acquisition, I believe. Translunar Acquisition, something like that. This is a burn that is going to allow the moon to capture us. And at that point, we are now stuck around the moon. If our rocket, for whatever reason, fails, we are stuck. At this point, we're still safe. But this next burn that comes up is mission critical. And if we don't get the right burn, we might lose the moon, but be stuck in an orbit around the Earth that is unfavorable to us. If we burn too long, we might inadvertently crash into the moon. And so we really need to know if this burn went well. The problem is we're on the far side of the moon at this point. We're out of radio contact with the Earth for this burn. So this is why astronauts had to be very skilled pilots, because this has to be done right. And they would actually time when they reacquired the signal from the astronauts, and basically the timing of that gave them the first indication of whether the burn went correctly or not. If they burned too long, it would take them longer to reacquire the signal. If they burned too short, they would get the signal quicker. So that was one thing, and then you would obviously check your trajectory more carefully once you're back in radio communication with ground control. So we have done that burn, I believe, and now things are going to start happening. We are going to transfer 2 crew members into our lunar lander. Or have I not done the burn yet? I looked away. Nope, we're still in insertion mode. Okay. So we're turning retrograde, meaning we are pointing away from our direction of travel. You can see we are heading in this direction, but we're going to fire this rocket to slow us down. And then you can see that changing our path, and eventually now we are in orbit around the moon, and we're going to bring that orbit all the way down to circular. Just about there. I'm asked what step are we on? Let's see here. So I'm actually skipping many of the steps because it would take me hours. We're on step 58. So we're just at service module engine cutoff, which is 59. 60, we begin our lunar orbit evaluation. That's that thing I was talking about, is are we in the right orbit? Are we safe? Are we going to crash into the moon? Are we going to lose the moon? In Kerbal Space Program, you get a nice little line around the moon that tells you you're fine, but in reality, you have to do a bunch of math to figure out if you're actually on the orbit you think you're on. So we're transferring our crew here into the lunar module. One person is going to stay behind in our command module so that he can take care of that spacecraft and make sure everything's running well while we go down to the moon. So we got our crew transferred here. We're now going to separate from the command module. And now things are getting real serious because now we have 2 different crew, 2 different spacecraft. The call signs for each craft have to be different so that you know who Mission Control's talking to and Mission Control knows who's talking to them. And now we're going to do a bunch of system checks on the landing module in preparation for the descent. We're going to do things a little bit different in Kerbal, but it's going to show you all of the same kinds of things. So deploying landing gear there, making sure everything's right. My landing craft a little bit different than the Apollo, which I'll point out a little bit later. And so now we want to pick our landing site. Now, for Apollo, this was already well established. They knew exactly where they're going. Again, I'm winging it. But I want to land somewhere near the terminator, the line between light and dark. And so you can see that on the moon here. This is the light side. This is the dark side. So I want to land somewhere right in this region here. That will give me those long shadows that I want. It will also keep me on the near side, the side facing the Earth, so we can have good communications. A lot of the planning for a mission is about lighting. Are you going to be able to see what you are trying to do when you need to do it? And you'll see this because we've separated from our command module. At some point, we need to rendezvous back with that spacecraft, and you want to be able to see what you're doing when that happens as well. So we have basically started. This is like the power descent phase of the landing. So we've brought our periapsis or paramoon, something like that, down to about 10,000 meters, and now we're going to float down to that level there. So we got lunar sunrise. We're going to fast forward just a bit. Diane, I'm not even going to try to pronounce that word. Parasynthian. Yeah, I just say periapsis every time. Perihelion is when you're around the sun. I think periapsis is technically supposed to be... no, periapsis is the general. There's an Earth one, too. And so I'm actually aiming to land right inside this large crater. I'm putting a maneuver node here so that I can time it out right. When we get to there, we're basically going to put the brakes on this hard and basically get just like a dead stop and come straight down onto the surface. And guys, you have no idea how many times I had to fly to the moon to get this all to work properly. Astronauts would always joke about how many times they were killed in the simulator. Yeah, I was killed in the simulator quite a few times today and yesterday, trying to make all of these maneuvers correctly and get a nice video for you guys to see. I'm hoping it's a little bit better than me just playing with my models. You can actually see the distance that we have to travel, when certain things have to happen, how the spacecraft has to turn around. So we are coming up on the actual final approach here, again seeing those thrusters working to point our spacecraft where we want. Absolute maelstrom of thruster activity there. And rotating around so our windows are facing forward. This is going to be a little bit simpler of a descent than was actually for Apollo. If you actually go to the recordings for the Apollo landing, you can hear the lunar module pilot calling out altitudes and angles. And this is basically, you know, what rotation is the spacecraft at and how high up we are. And this is giving them the profile that they're trying to follow down, and they'll know if they're on it or off of it based on when those numbers are coming out. But for us, again, we get to just kind of wing it. We're just going to slow down. We've got a really nice view. We can see everything that we're trying to see. Imagine trying to do this while just looking out of those very small windows on the lunar module. It would be much scarier, to say the least. But that red dot there indicating where we're probably going to come down. So this is where it gets really hair-raising, because any mistakes now are life-threatening. If we do an abort, we will separate the ascent stage and basically just come right back up to the command module. But you don't want to have to do that. All the other astronauts will make fun of you if you have to abort on the landing stage. So I want to land in this crater because it's giving me the right shadows, and I'm going to have a nice flat spot to land in. This is a large crater with craters inside the crater, so it's not like we're landing in a big hole. We're actually going to land on a nice flat spot between a bunch of holes. And I believe you can see the shadow right over here. This is what we would be watching out the window as we come down, checking that everything is as it appears to be. And this is the main reason why we are landing during this time on the lunar surface, is just so that we can see that shadow. So the sun is to our back, illuminating where we're looking. And so looking up here, we're at about 800 meters above the surface. We're basically pointed straight down, and so now we're just going to do our final float down. And you can also look at our surface velocity right here. So we're falling at about 9 meters per second. So you'll see this number fluctuating as this number is going down as I'm throttling this rocket. In fact, this rocket right here on the descent stage of the lunar module is probably one of the most impressive pieces of hardware. This rocket has a gas pedal. You can adjust how much thrust this rocket is putting out. I think all the way down to about 30% of its total. Most rockets do not do that. Rockets are on or off. And so this one being able to adjust how much it's thrusting was a bit of a technological challenge and a very impressive feat of engineering. We are getting really close to touchdown here. Yes, Betsy, lighting is everything. And this, it's not just the moon. When we talk about, orbiting an asteroid, I actually wrote a paper on the Psyche mission that's coming up. And there was a lot of back and forth about, what planets do you want to fly past to get gravity boosts from? But the most important aspect was time of rendezvous, because the asteroid rotates in a certain way, and so if you go there during this time, you could see the entire thing illuminated by the sun as it rotates. But if you get there 6 months from now, it'll be in an orientation where you only see half of it. Really, so choosing the locations or the timing of when you go to certain places is really important. So we have landed, one astronaut out. Here comes our scientist. You can see the front there of the lunar module in shadow, just like the original Apollo photos. And now we are going to plant our flag. He's going to walk around there. The adorable little Kerbel people. So my lander legs are off to the side of my ladder, which is not the way the actual Apollo lander was built. I just couldn't get it to work in Kerbel. It was much easier just to put some separate legs on this guy. There we are. Yes, Diane. Everything in Kerbel is much faster than it is in real life. When they landed on the moon, the first thing they did was there's all these checks. So there's go for power descent, then there's go for landing. Then once you land, there's a stay, no stay. And everyone has to agree everything is working properly, we can stay on the moon. Once they get the go for stay, they have to do a bunch of other checks, and it takes them quite a while to actually put on all the other things they need on their spacesuit and to get ready to actually go outside. One of my favorite little fun facts from Apollo is that they could have locked themselves out accidentally if they closed the lunar module door from the outside. So they were very careful to leave the door open so they could get back in, which we are now back in the spacecraft. So now we need to rendezvous back with our command module. Now, we haven't actually stayed on the surface very long, so we're just going to hop right back up to that guy. But in reality, you would have to kind of wait. Like I said, they were on the surface for much longer than the 5 minutes we've been here. They were on the surface for several hours. And so the command module is going to go around several times. They're going to wait for the perfect timing to come back to save as much fuel as possible. But again, in the tradition of Kerbal Space Program, we're going to wing it. So now we are going to separate and launch our ascent portion of the lander. Here we go. Any moment now. All right, and we are off. We are now a very small and light spacecraft. It doesn't take much fuel or power to get us back where we need to go. That descent stage is going to stay there for all of time as a monument to what we have done. We are going to turn down to the west and go back into orbit. You may have noticed that we've lost quite a bit of our spacecraft since we've started. This is before the days of reusability. Very few things come back from the moon. You would basically leave everything besides the rocks that you picked up, which included waste on the surface. And in fact, once we rendezvous, we're going to fill this puppy up with even more garbage before we jettison it around the moon. So, getting back into orbit, you can see us getting higher and higher here. This is probably the most difficult portion of the mission, at least for me, recreating it, because rendezvous is just never easy. There are so many things to go wrong with rendezvous. And let's see if we can jump ahead here a little bit. Let's watch the moon go by. Because this spacecraft here cannot get us back to the Earth. It cannot survive re-entry. It doesn't have enough fuel. We need to get back to the command module if we have any hope for survival. No, there's a lot of littering on the moon. We have polluted the moon more than once with all manner of either crashed spacecraft or human waste. There's even some tardigrades, which are a very hardy single-celled organism. They're encased in resin, but potentially could be revived in the future, which is pretty interesting. I still don't understand why they took those tardigrades to the moon, but so is the flag still there or disintegrated? So the flag is most likely still there. Unfortunately, on Apollo 11, when they fired the ascent motor, it knocked the flag over. So the flag is in the lunar regolith. Some of the other flags survived. However, they are subjected to several hundred degrees of temperature during the lunar day, and the theory is that they've probably baked white by now, so there's a bunch of just white flags on the moon, and you probably can't tell that they're American flags anymore, but they're being bombarded by little micrometeorites, but it's going to take tens of thousands of years for them to disintegrate to any level. But it would be really interesting, and it wouldn't surprise me at all if the Artemis program goes through, that they visit a Apollo site to see what condition they're in. And that would be amazing to see some space hardware that's been on the moon for 50 years. So we're matching our orbits here. This is just going to help me make a rendezvous. But you can see when I change the view slightly that we are behind the command module. So that means we need to go faster than them to catch up. And in orbits, faster means lower. So we're actually going to bring our orbit down just a little bit on one side, and that's going to catch us up. And I want to catch up at a particular point. I want to catch up to this spacecraft while I'm in sunlight. So I have to do all of these maneuvers planning to be where I want to be for the right conditions. I just watched that movie not too long ago. Someone made a Big Lebowski reference. I just stopped in to see what condition my condition was in. And the condition is good right now. So you can also look up here. We have delta V current and total. So this is the amount of delta V, which is how much I can change my velocity by before I'm out of fuel. And so I have 65 meters per second. It's hard to intuitively know how much that'll give you in terms of, like, is that enough to return to Earth? The answer is no, but it's enough for this rendezvous. We should really only need, less than 50. All right, let's speed this up just a little bit. I want to hop to when I'm actually going to make this next burn. So I'm on the day side of the moon. This is where I want my rendezvous to happen. So I'm now burning retrograde, bringing this orbit down on the other side of the moon. And you can see these orange lines are my rendezvous intersection. And so I'm looking for the minimum separation between the two craft. So you can see those two coming together here. And right about there, I'm going to stop it. We'll jump another 30 seconds. You can see how I've lowered this one orbit as compared to the command module's yellow orbit. And so that circle ellipse is smaller than the yellow one, which we're not actually traveling the same speed, but just think if you were traveling the same speed, you would make the loop faster, right? And so this is basically how we're catching up. When I go lower, I actually also go faster, which helps you catch up. And so right here, I'm on the opposite side of the orbit. I'm trying to just fine-tune this rendezvous to be as small as possible, and I get it down to 1.6 or 1.7 kilometers. Not ideal, but good enough. So now I'm going to float until we are at that rendezvous. Go a little bit faster. And what we're going to do is so I'm one person making this video. In reality, you got 3 astronauts working on this. And I am not exactly sure who did the docking. Does the command module stay exactly where it is and the ascent part of the lunar module move and dock into it? Or does the lunar module get into some sort of orientation and then the command module take over? I don't know. That's how I actually did it. I have more fuel for this maneuver in my command module. Okay, Diane says command module pilot. That's kind of how that's how I did it. It makes sense to me. You have more fuel reserves in that spacecraft. Is that why they did it? I don't know. They may have had several reasons for why that was the procedure. Like I said, all of this stuff is much more complicated in reality. So we are now at 1.7. I have slowed down. I have jumped over to the command module, and I'm going to use this one to actually dock with the spacecraft. And so you can see here, this is our target now. That is the lunar module coming back to meet up with the command module. We have a lovely lunar background to see this thing against. This is one of my favorite videos from the Apollo era, is the ascent stage coming back up for rendezvous. Try to Google it. It's an awesome time lapse that they have of this thing kind of just coming out of the void. Great little piece of video. And we're floating in at 4.4 meters per second, pretty slow. We're now under a kilometer. I'm turning on my docking radar. And so now I want to get the attitude or the position that this spacecraft is in ready for docking. And that involves lining up all of these things, getting the rotation correct. And you can kind of see when these jets are going off, it's kind of bumping me all over the place. And it's not easy to get the spacecraft where you want it when you want it. And I can't tell you how many times you'll be doing this and it takes you too long and you fall into the nighttime side of whatever object you're orbiting around, and now you're lost in the darkness unless you've put lights on your spacecraft. There were lights on the Apollo spacecraft, but I don't have them for this mission, so I had to get it right the first time. The other reason that you want to do things in the light, at least for this mission, is if it wasn't in the light, it wouldn't be much good for you guys to look at, because it would just be a black screen with spacecraft just moving. So I wanted to do things where you guys could see them, and that actually matched up with the regular Apollo 11 flight plan pretty much seamlessly. They also wanted to do things in the light. So almost every part of the operations were done when you could see things. Yeah, the moon is about a quarter the diameter of the Earth, about 2,100 miles. Yes, Diane is 100% right. 1/4 the size and 1/6 the gravity. And that confuses some people, because you'd think, well, if it's a quarter of the size, why isn't it a quarter of the gravity? But the problem there is that's not how spheres work. Spheres are, if you do the volume of a sphere, it's 4/3 pi r cubed. So when you half the size, the volume goes down by a cube. I'm rambling. So in terms of mass, the moon is much less massive than a quarter of the Earth. The other problem is surface gravity. Calculating the actual surface gravity depends on the density and radius that you're talking about, and so you do all those calculations, it comes out to about 1/6. It's another interesting little calculator I should build. Like if you were standing on top of a mountain that was as tall as the ISS flies at, how much would you weigh compared to what you weigh at sea level? And the answer is something like 99% of what you weigh at sea level. All right, so we're getting pretty close to docking here. I'd love to do this faster, but this is kind of stuff that you just have to take your time and do right the first time. Because if you bump things and they start tumbling through space, it's just not fun. So my mother is asking, how high are you to see the curvature? 50,000 feet. 50,000 feet would probably do it. That's like Concorde levels of altitude. And I believe people at least claimed, I never flew Concorde, but they said that you could see the curvature flying Concorde. So yeah, you don't have to go too high, but it's going to be easier the higher you go. So if you could get to 70,000 feet where a weather balloon goes, it's much easier to see that curvature. But it's really cold and there's no oxygen, so plan ahead. All right, we have rendezvous. So now we are going to transfer our crew back into the command module. We're also going to now take all of the garbage from the command module and stow it into the lunar module for jettison. This includes the lunar spacesuits. Most of those were jettisoned. A few of them were brought back from museums, but most of them went back into the lunar module to be jettisoned. Now, in Kerbel, when we jettison this, it's going to float around the moon forever. But because of the lumpiness of the real moon, the lunar module's orbit would quickly decay and it'll impact the moon in like less than a day. So all of these ascent vehicles here you see in green, all of those are wreckage sites somewhere on the moon. And we actually don't know where they are. So this will be another cool thing that maybe Artemis will be able to do when we go back to the moon, is to look for these wreckage sites. All right, I am transferring some propellant and stuff out of this vehicle before I jettison it. I want all of the possible fuel because I don't exactly know how much I need. So we're going to transfer that, and now we are going to jettison this spacecraft. Go for undocking. So that is now more junk and less spacecraft that we are coming home with. So we're going to let that guy float away, and like I said, in the real world, that guy would be impacting the moon in a day or so. I don't remember how much altitude they actually lose on every orbit. It's something I used to know. It's a lot. It's more than you think it would be, which means that they had to. That's one of the reasons why they have that 110 kilometer orbit above the moon, is to keep it stable for longer, the period of time that they're going to be there. Couple of months, Diane. Really? Okay, I'm gonna go into my book and find the values, and can figure out, how long it would take. But suffice it to say, they're all crashed on the moon by now. So now we are designing our return. So this is one of the most important firings of that service module engine. If this burn does not take place, we are stuck around the moon. So we transferred our crew. So when you saw that little spacecraft separate, no one was on board, just junk. Everyone is back inside the command module right here. So we are now moving our attitude for this burn, and now we're going to fast forward. Let's just jump ahead here. Let's see. All right, so now we are burning to leave the moon, accelerating away from it. You can see that orbit getting longer and longer. Eventually it'll leave the moon, and now it is helping us come back into the Earth. We're going to drop our perigee all the way down to where it actually cuts through some of the atmosphere. And then we're on the float home. And all of the same rules applied when we were floating out to the moon. We're going to be doing star sightings, radar checks, telemetry, positioning checks, and then we're going to be doing some mid-course corrections. When we're not doing that, we're going to be in that thermal control role, and we're going to be taking some rest periods and trying to sleep. It's a 4-day coast home. This is called the long fall. We are literally falling back to the Earth. And so now back in the thermal control role there just to show it. But when I fast forward through time, in the game, it freezes the spacecraft. So you'll just have to imagine that we're still rolling there. Our beautiful little command service module there. All right, let's get going. So leaving the moon at 50 times regular speed. And like I said, this is not the Earth-Moon system. This is the system in Kerbal Space Program, which is a little bit smaller than our system here. It makes the flight time shorter. It makes the fuel consumption less. It just overall makes the space flight a little easier to do, which is nice when you're just trying to play a game and not doing all the real world stuff. Because man, you put the game in the real system and just getting to orbit becomes very difficult. Jonathan, I did not forget the lunar module Kerbels. They were transferred. It didn't show, and there were some other little things I missed. On our float back, I've paused it here, but on our float back from the moon, we actually need to do an EVA out of the command module, because on the real lunar service module here, on one of these sides, there was actually cameras that used film rolls. And so you had to physically go outside of the spacecraft, remove this canister of film, and bring it back onto the command module here. And there are some awesome photos of one astronaut who's got his head just kind of poking out of the command module here, while the other one is shimmying down the side of the spacecraft. And one of my favorite stories, Diane will have to tell me which crew it was. It was the one Mattingly was flying on. And one of the astronauts had lost his wedding ring at some point during the mission. And so it was just one of those things like, and so while this extravehicular activity was going on, when they have this huge door open and an astronaut standing in it, he saw his buddy's astronaut, wedding ring floating, and was able to actually grab it and stow it away. And so when the other astronaut came back in, he let him know that he found his wedding ring. I just think that's the coolest story. And Diane is telling me it was Apollo 16. So thank you, Diane. So let's continue to play this. So there's, like I said, this mission is just giving you the nuts and bolts. There is a lot of other things that are happening during these flights. They are nowhere near as simple as what we are showing here. But at this point, we are coming back in to the Earth's sphere of influence. We're getting close to home, and so now it's time to jettison the service module. This is where most of the consumables, basically where your power and air and water is stored. So when we separate from the service module, it's time to come home. And if anything goes wrong now, like it's about to, it's going to be bad news for us. So I'm going to jump another 30 seconds. Let's get into the atmosphere. So that service module, it's just going to burn up in the atmosphere. The way that we separate it was not true to Apollo flight. They turned at a 45-degree angle to try to get this thing to separate, because they were much more concerned about collisions than we are. I'm pretty much guaranteed to not hit the service module on re-entry. But with the real spacecraft, it was unknown exactly how this thing was going to fly through the air. And in fact, astronauts did see the service module come and fly past them while on re-entry. So there were times when the possibility of a collision was not zero, which is a scary thing to think about. You've come all this way, you're re-entering the Earth's atmosphere, and then you're impacted by your own service module. So what's happening here is we are entering the Earth's atmosphere, slowing down using air resistance. The actual Apollo spacecraft could just roll itself around, and that was enough to actually control it. It basically pitched in one direction, and then they would rotate it to steer the spacecraft. So if you rotate it in one direction, you would kind of dip down into the atmosphere, and then you could rotate to the left, to the right, up or down. And so that is used to try to land as close to your recovery craft as possible. That is another thing that we don't have to worry about. So we're just going to hang tight and just float. But what's happening here is we're actually not slowing down enough. And so what's going to happen here is we're going to skip off the atmosphere. This is something that you don't want to do. If we were a real Apollo crew, we would basically be dead because once you skip, even though we're going to come around in this orbit and enter the Earth's atmosphere, we would probably run out of supplies during that time. So that would be bad for us. So I'm just going to fast forward back to falling into the atmosphere. And we're going to get the rest of this mission done. So another critical part of the mission is the parachute deployments. They have been in space for nearly 2 weeks now, being heated, being cooled. So let's hope that everything was done right with those. On the real Apollo spacecraft, there is a upper heat shield that covers the drogue chutes and main chutes. So during this part of the reentry, they're not subjected to any of that heating. Once we actually get through this ionization portion of the descent, we would jettison that cover, and then at about 7,000 feet, our drogue chutes would go out. Drogue chutes are basically just high velocity parachutes that'll get you slowed down enough to where you can release your main chutes. Again, in Kerbel, we don't really need to worry about this. I just use one chute as a drogue and then release the other two. But we're floating down pretty fast here. Again, tracking our altitude, velocity. We even have a G sensor here. And so I'm just pulling up that one parachute. I think I deployed it somewhere around 10,000. And we're landing into water because even with our parachutes, we're going to be coming down pretty darn fast. And the landing, it looks soft, but in reality, it's quite a jolt. There were missions where seat posts broke, people's vertebra got kind of compressed, people have been injured on reentry. All right, we are 2,000 feet away from home sweet home. At this point, the atmospheric pressure would have equalized and ambient air would have been fed into the command module, which would probably be a nice feeling after having canned air for 2 weeks. And now we're on the final float down. So I'm speeding this up a little bit here. I just want to get home. So this is how you do an Apollo flight in about an hour. The real ones took at minimum about 10 days. Getting a little choppy here, not sure what that's about. And splashdown. All right. And then we wait to be rescued. So again, this is why you needed to try to steer as close to recovery vessels as possible. If something went wrong and your reentry profile was screwed up and you landed, 100 miles from a recovery ship, you have to wait in this capsule for that ship to sail out to you, which would probably not be pleasant. Diane, I don't have orange floaties. Yeah, so Diane is referencing, if you look at the actual Apollo pictures, there's a flotation ring around the spacecraft and there's little bobbles on top of it. These were inflatable things to orient the spacecraft when it touched down. So imagine, you've got this triangular capsule. If it landed in the water in a weird way, it could flip upside down. These floaters would turn it back right side up so that you could get out of the darn thing. Once again, something you don't have to worry about in Kerbal Space Program. The thing that I love about Kerbal is that it makes you appreciate just how difficult real space flight is, because you notice all the little things it's doing for you and all the things that you don't have to keep track of. In the mode that I play in, there's infinite air in the spacecraft, infinite food. You can send a Kerbal out into space for a decade and he will be just fine in a spacecraft that's tiny, and they're not claustrophobic people by any means. They will stay in a very small capsule as long as you tell them to, which is another thing you can't really do with real humans. And so just thinking of like the Apollo flights and how long they stayed in that pretty small capsule is something that probably won't be replicated with the Artemis program. It's going to be much roomier, I suppose. But that is Apollo in a nutshell. Like I said, it's so much more interesting than that. Here is the list. So we didn't go through everything step by step, but I don't think you would want me to. It would have taken 3 hours because every little thing I would be like, oh yeah, and there's a really interesting thing about that. We can maybe do a deep dive on certain aspects of this list. And this is the simple list. It's really much more involved than this list. If you guys are interested, this book right here is one of my favorite books. I often reference this as my Bible, except for the fact that Fundamentals of Astrodynamics is actually my Bible. But How Apollo Flew to the Moon by W. David Woods is absolutely fantastic. I've got a bunch of bookmarks in here of things I wanted to talk about, but this really breaks down Apollo flight just so well. It has a detailed, section about just every single operation that's going on. I wanted to talk about this tower jettison. There's 3 different abort scenarios depending on the altitude and velocity that you're at for the tower jettison. I could talk about it all day. They break down, how star navigation works. They break down components of the spacecraft, and also like little mission details, like the stories I told. That all came from this book. Finding the S4B as an asteroid on I think 17. Hilarious. And then it basically breaks it down by section. So pre-launch, launch, translunar insertion, coast, deciding to stay. No, what is it? Coast, entering moon, deciding to land, exploration, rendezvous, the fall back home, and then re-entry. And so like each one of those chapters is just full of just exactly what they had to do and when. So one of my favorite books right here. And I'm actually not finished with it, but great. Why? Oh, I can't bring back rocks in Kerbal. I actually can. You can do sample. There's like I said, it's a game, so there's a lot of little sciencey things you can do in there. You don't have to do them, but technically you can pick up rocks and bring them back and get credit for them, which is fun. Whew, man. Well, that went much better than it did last night. I hope you guys like this. It was probably a little boring to just watch the video. You know, maybe I should have done one where I just play with the models, because that could also be fun with me. You know, showing the attitude of the spacecraft changing as you're going into power descent, pointing out all the little nooks and crannies on these spacecraft. But Lego didn't build me a command service module. I only have the lunar module. Lego, get on it. I want the matching piece of the spacecraft. All right. But this has been the longest video by far. We are at an hour 13. So if there are any final questions, I'll be more than happy to answer them. But if not, I am going to sign out and try to figure out a topic for next time. I'm thinking maybe telescopes, do some more interactive stuff, because I actually have one of all the basic different types of telescopes, and so we can talk about one type over the other, what to look for in a telescope, what to look at with a telescope, all kinds of stuff like that. So that might be the next one. All right. This is me signing off.